All right, I want to talk about electron configuration diagrams, and specifically right now I want to talk about how what you see in electron configuration diagram relates back to what you learned about when we talked about quantum numbers. So first things first, we have our principal quantum number very evident in our electron configuration diagram. So the fact that we have a 2 here and a 2 here, that's our principal quantum number. We know n equals 2. And that also can be called the shell. So 2s and 2p make up our second shell. For the third shell, it's 3s, 3p, and 3d. So there's more and more subshells, brings me to my next point, added as we increase our principal quantum number. So our subshell is going to be our second part of our label. And we know about our L values now. So we can say, well, that's L equals 1, but oftentimes we call that the subshell. Just as a quick reminder, we can hold a max of 2 electrons in our S subshell. And then, for instance, our P subshell has 3 different orientations. So we can only put 6 electrons in there. The order of this is important because it corresponds to the increasing energy levels of the subshells. And we're always going to start at the lowest energy level and fill upwards. I want to introduce the rules individually as we work through some of the problems. And so the first rule is the Pauli exclusion principle. So Pauli told us that there's unique quantum numbers assigned to each electron within an element. So we can't have any repeats. So to avoid repeats, right, because if you're at the 2s level, we have an n equals 2, L equals 0. What distinguishes between those 2 electrons? Well, that's going to be our spin quantum numbers. So we can attribute those to Pauli and the Pauli exclusion principle. Therefore, electrons in the same orbital have to have opposite spins. And if we're in a situation where there's multiple orbitals of the same energy level available, then we're going to do same spin, same spin, same spin. So each one of these lines is called an orbital. And it holds a max of 2 electrons. The electrons themselves are represented by arrows. And so we can do a full arrow like this, but oftentimes we wind up doing half arrows, just maybe out of laziness or something. And when we talk about opposite spins, or you could do like full-headed arrows like that. Alrighty, so let's do the electron configuration for carbon. I'm going to show you a couple different methods of approaching this. So carbon has 6 electrons. So I'm going to start in the bottom here, and I'm going to put my first 2 electrons, and I want to make sure they have opposite spins. So 1, 2. Then I go to the next available subshell, next lowest energy. I have 3, 4. And now I'm going to do single filling, but with the same spin. So we got 1, 2, 3, 4, 5, 6. Those are carbon's 6 electrons. And so they're going to occupy 1s, and then the exponent here represents the number of electrons in that subshell. So we're going to do 1s2, 2s2, 2p2, because there's just 2 here. And then if you add up the exponents, you could double check. That's 6, right? Phosphorus has 15 electrons. So I'm going to just build off of what we have here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And so when I write that one out, I'm going to write 1s2, 2s2, 2p6, 3s2, and in that last subshell that we filled, the 3p, or it's not filled, it's only half filled, we're going to do a 3p3 with that one. Next, we have the Aufbau principle. It's German for building up, and this principle tells us that we're going to completely fill our lower energy orbitals or subshells. So we're going to put 2 electrons in the 1s before we even think about putting any electrons in the 2s, and so on and so forth. So let's see how that applies. So we have argon with 18 electrons. That's based off the atomic number on my periodic table. So I'm going to come over here. I'm going to do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So we worked our way from the bottom to the top. And this will turn into 1s2, 2s2, 2p6, 3s2, 3p6. We can double check our work. If you add up the exponents, so 10, 11, 12, 18, that should equal the total number of electrons, especially when you're writing these full electron configurations. Neon has 10 electrons. So we need to get rid of some electrons here to kind of see what's going on with neon. So on neon we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm going to write 1s2, 2s2, 2p6. And that's it for neon. The last rule is Hund's rule, and Hund's rule tells us that electrons are going to fill singly within the same energy level before they start doubling up. When we have orbitals of the same energy level, so for instance 2p has 3 orbitals, and we know they're the same energy level because they're all in the same horizontal line. So when we have that situation, these are known as degenerate orbitals. So let's just see a couple more examples, and see where Hund's rule might apply. So nickel, now we have something with 20 electrons, and we're asked to write a full electron configuration. So I'm going to start Aufbau principle, right, top to bottom, and do all 28. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I'm in the habit, you'll notice as I'm filling this out, that I just automatically apply Hund's rule. So 12, 13, 14, 15, a bunch of singles. Now we start doubling up. 16, 17, 18, 19, 20. Here's another odd thing that I wanted to point out. You go from 3p to 4s because we're going from top to bottom. So the next lowest energy level after 3p is the 4s. Then after the 4s, then comes the 3d. It's kind of weird, but just always double check, and I'll show you a couple other methods in a minute here, but always double check that you're going in the right order of energy. So I was at 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. And that's, we did all singles, and then we went back and started doubling up, but there are some half empty orbitals there. The D, just as a reminder, has 5 orbitals, so it holds a max of 10 electrons. Alrighty, so let's turn this into just like a linear notation here. So I'm going to do 1s2, 2s2, 2p6, 3s2, and then after 3s2 is my 3p6, 4s2, and then 1, 2, 3, 4, 5, 6, 7, 8. There's 8 in the 3D. I usually write it like this, and it's perfectly acceptable because there's no ambiguity here. This is the correct set of orbitals with the right number of electrons in each one of those subshells. However, what you're going to see on ALEX and oftentimes in textbooks is they like to keep the same shells or same principal quantum numbers together. So instead of writing 3p6, 4s2, 3d8, they'll rearrange this to finish up the 3. So they'll do 3d8, and then they'll put 4s2 last. But at the end of the day, same difference. Don't worry about it. Just as long as you have them all listed and you have the correct exponents, you're good to go. So strontium has 38. So we're up to 28 here, right? So we're going to do 29, 30. After 3D, so it goes 4s, 3d, and then 4p. So we're going to put another 6, 30, 31, 32, 33, 34, 35, 36, and then the 5s, so 37, 38. Strontium has its last electrons in the 5s subshell. All right, again, let's write this out. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, and 5s2. And it may be presented where all the same shell is together. So 1s and all the 2s are together. So I'll do 3d10, 3p6, 4s2, 4p6, 5s2. Either way, all these numbers should sum up to 38. So I got 2, 4, 10, 11, 12, 22, 28, 30, 36, 38. So as we saw earlier, writing the electron configurations of some of our larger atoms can be kind of tedious. And so we have what's known as a noble gas configuration, and that's in contrast to the full electron configuration. So your noble gas configuration is an abbreviated version of the electron configuration. And what you're going to do is, say you're writing the electron configuration for phosphorus. You're going to pick the noble gas, so the group 8A compound that's closest but smaller than the element of interest. So for phosphorus, the closest one, it may seem like it's argon, but it's not, because it has to be smaller. So I'm going to select neon as my abbreviation. And so that means every electron associated with neon is understood, and we just have to worry about the last handful of electrons when we're writing that electron configuration. The second thing that I wanted to introduce, apart from the noble gas configuration, is what's known as the block method. So instead of drawing an electron configuration energy diagram and filling it all out every time, we can extract the patterns that we see on that diagram just by looking at the periodic table. It's really, really amazing. So I recommend you have a periodic table handy. as you're going through this. Groups 1A and 2A of your periodic table are known as the S block. The S block is nice in that the number out front, the shell number, is going to correspond to the row number. So in here, this is 1S, and then this area in here is going to be 2S, 3S, 4S, so on and so forth. P's, we saw a lot of P's in our previous segment. The P block is over here. The other thing about the blocks, we know P's hold 6 electrons. If we count, and we're just looking at this section, we have 1, 2, 3, 4, 5, 6 elements going across on a given row. Like the distance from here to here has 6 elemental boxes. And so in here, and it continues down here, all of this is our P block. The number out front on the P's also corresponds to the row number. So we don't have a 1P, we just have 1S. And then we have 2S, and then over here would be the start of the 2Ps, and this would be the 3Ps, and so on and so forth. D block is in the middle. If you count across, D orbitals combined hold 10 electrons, and if you count, you get 10 elements going across in this center section. So this whole thing is your D block. Just be careful with the D block. Remember, it comes out in kind of a weird order. So we saw in our previous examples, we did 3p6, and then the next thing, and look at your energy diagram maybe, the next thing after that is 4s2, and that's right here, and then we see 3d. So what I like to say about the D block, you're in the 4th row and you hit 3d. You're in the 5th row and you're gonna hit, so your 5th row, you're gonna hit 4d. And in your 6th row, you're gonna hit 5d. So the D block lags one behind. So whatever row you're in, your D block is gonna have a number out front, a shell number, a principal quantum number, that's one less than the row number. F block, I don't emphasize the F block too much in any of my courses because there's a lot of exceptions and weird things that happen in the F block. But just for your knowledge, F orbitals hold 14 electrons. So there's, in the F block, we have a total of 7 orbitals, and you can figure that out by looking at that energy diagram. There's 7 lines, there's 7 boxes, and that holds a max of 14 electrons. And our F block is down here with our inner transition metals, and it lags 2 behind. So we first see the F block in the 6th row of the periodic table, but we wind up with 4F and 5F. So it's going to go something like this. So 6, and then you're going to go down here, and then you're in the 7th row, you do 7S, and then you can access the 5Fs. Again, it's very weird, and I don't like to emphasize the F block too much because the order of filling is slightly weird too. Let's use the block method to come up with electron configurations for bromine, phosphorus, and germanium. First thing we need to decide is what noble gas are we going to use. So for bromine, krypton is the closest noble gas, but it's larger. So remember, with noble gas electron configuration, you always have to go smaller. So I'm going to select argon. And that means the first 3 rows, everything up to argon in terms of the electrons is taken care of. That leaves me at the fourth row. So I'm going to start with 4s1, 4s2. So you're just going to go across and count within the box. So 4s1, 4s2, I wrote that down. Now I'm at 3D, and I'm going to need all 10 of these. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 3D10 is completely full. Now I'm back to 4P. So it's going to be 4P1, 4P2, 4P3, 4P4, 4P5. Phosphorus is in the third row. So I'll go back up to neon and use that as my noble gas. The noble gas, for the abbreviated one, always needs to be in square brackets, and you can only use a noble gas. So that takes care of the first two rows, leaving me at the third row. So I'll do 3s1, 3s2. And this isn't drawn to scale. Make sure you're moving along with your finger on your periodic table. That looks a little bit better. So after we got 3s2, we have 3p1, 3p2, and phosphorus is in the group 5, right? And so it's the third one, so 3p1, 3p2, 3p3. Germanium, I'm going to use argon. So I'm good to go through argon. Now I'm going to do 4s2, all of my D blocks, so 3d10. And then 4p1, 4p2. And that completely takes care of the germanium. Another aspect of this to consider is our valence electrons. So valence electrons are defined as the electrons with the highest n values. It doesn't matter the energy level. It matters what is your n value out front. So for instance, with bromine, we have 4s, we have 3s, we have 4s. So since 4 is higher than 3, the valence electrons are going to be associated with the principal quantum number of 4. So I have valence electrons in the 4s subshell and the 4p subshell. 2 plus 5, I have 7 valence electrons, which you would have told me prior to this because bromine's in group 7a. So these are both part of my valence. And then the rest of it, the argon is what's known as the core. And it takes a lot of energy to mess with the core. So typically they don't see disruptions in core electrons due to like redox reactions or bond formation or anything like that. This is also part of the core. It's super stable because it's a full subshell. So it's going to be hard to disrupt that as well. With phosphorus, we're fortunate in that we only have one principal quantum number written here. So everything here, the 3s2 and the 3p3 are considered valence. Here in the germanium, we have that comparison situation again. So 4 is bigger than 3. So I'm going to put the 4s2 and the 4p2 as my valence for a total of 4 valence electrons. The 3d10, that's part of my core, and so is the argon. Let's practice a little bit more. So first, zirconium, which is in the 5th row of the periodic table. So my closest but smallest noble gas is going to be the krypton. That takes care of the first 4 rows of the periodic table. So on the 5th row, I'm going to do 5s1, 5s2, And then after that, I have 4D1, 4D2. Indium is also in the 5th row of the periodic table, and we'll use the same noble gas thing. We'll use the krypton again. Again, I apologize if my drawing here was difficult to draw. So 5s1, 5s2, and then we need that whole D block. So we'll fill it up completely. D's are one behind. We're in the 5th row, but we're going to do 4D10. And then the indium is right at the start of the P block. So the D block has the 4 out front, but when you get back to the P's, you're back in line with your row number. So I'm going to do 5P1. A couple of examples where we start using the F block or come close to using the F block. So lanthanum is in the 6th row of the periodic table. I'm going to use xenon as my noble gas. And so 6s2 is gone, right? So we get 6s1, 6s2. This is a D block, so I'm at 5D1 with that. The F block is super strange. So honestly, there's so many exceptions, and they're not very predictable with the F block. So I would definitely Google electron configurations of these. Look at a couple decent sources, compare what they say, because they do a lot of weird things down there. So for instance, the first element here is going to do 5D1 for F1. But then at some point, the D goes away and you just use F's, but it just flip-flops back and forth. However, by the time you get back over here with lead and bismuth, we don't have to worry so much about the weirdness that goes on in the F block, because it just gets filled up and we just write it down, and we don't have to worry about the order of filling as much. So for bismuth, I'm gonna do xenon and 6s2. Officially, the F block would come next, right? So I'm going to use my entire F block to get over to bismuth. The F block lags 2 behind, so I'm in the 6th row, and this is the first time we see F subshells. I'm going to do 4F14. Then I go back and I start doing my D's. I need all of my D's. So 6th row, D's only lag 1 behind. So I'm looking at 5D10. And then back to the row number for the P block. So 6P1, 6P2, 6P3. Let's discuss really briefly here, who are our valence electrons? So for zirconium, our valence will be the 5s2, and everybody else will be part of that core. For the indium, it's going to be 5s2 and the 5p1. For lanthanum, it's going to be our 6s2. And for bismuth, we're going to do our 6s2 and our 6p3. Why do I emphasize the valence electrons at this point? Our next step here is going to be to talk about ions. When you form an ion, you remove your valence electrons first.